until now, completed the drilling, lapping, and seat grinding processes on our pump. We're going to check the trigger distances. One of the most important things to pay attention to during this check is the cleanliness of the pump surfaces and making sure the edges of the plates are free of burrs and not dented. Because if this surface isn't clean, it leads to errors when measuring the trigger distance. And this is where a lot of major mistakes happen. The intermediate plate is removed. When it's carelessly tossed around, dents occur on the edges and corners. When the trigger distance is measured from here, since the surface doesn't sit flush due to not being properly aligned, it causes errors in triggering. So, what do we need to do about this? When we get down to the surface, we have plates located right here. At the very bottom, there are plates with 800 grit, 1,1200 grit plates available. The best one is the 1,000 grit plate. We check whether there are any burrs on its surface or not. We place the plate. We draw a figure-8 pattern like this and observe. It should stick completely to the surface. We can even tell if there's the slightest burr just by the sound. There are no burrs. We also check the backside. It's perfectly fine, no burrs. Let's say there are burrs. Instead of grinding the surface like this, we can also lightly hold it and, while pulling it with a gentle curve like this, as we curve it, the burrs on the edges can be removed like this. We can remove them this way too. Yes, we've cleaned it properly like this. Now, the measurements of these plates are also important. The original measurements of the plates come out to 7.98. But others grind or sand them. One side measures 7.98, the other side comes out to 7.95. In such cases, you're working with different measurements from each corner of the square plate. We measure its parallelism using a sensitive micrometer like this 7.98 millimeters. The standard measurement is 7.98 millimeter. You need to check this on 3 or 4 sides to make sure the parallelism is correct, right? 7.98 millimeter within 1 micron. And if there are small burrs on the surface, we handle that process like this too. We take the diamond plate, flip it over, place it down gently, and press from the center. In a crisscross motion, look, see how nicely it fits on the surface. You can tell by the sound. First like this then. When we do it diagonally like this, if there are any burrs or dents on the surface, it completely removes them. After that, we place our plate into position. It sticks very nicely. We had already fitted the 7.010 valve earlier, and now we've installed it. We're installing our 7.010 valve. It's square plate. Of course, after installing this valve, the valve should be able to drop down smoothly. It shouldn't get stuck. Let's check that as shown. For example, we're working smoothly with the 7.010, but if the 7.015 doesn't go in at all when you try to install it, then the 7.015 isn't fitting. If the 7.010 operates smoothly, that means a working clearance of 3 to 4 microns has formed. The required working clearance value is around 3 to 4 microns. We installed it and made sure it sat flush with the surface. Then pressed down the valve. Here, we have a gauge to measure the triggering. We're also zeroing this gauge properly on the plate. Yes, it's zeroed. When we press the valve from underneath, it moves upward. And we take the measurement. It reads 110 micron. We measure from here. Again, 110 micron. We check again from the side. 110 micron. 110 micron. The measurement parallelism is very good. This measurement is the value it should be. In the original ones, it reads between 110 minus 120 micron to keep the fuel amount high here. It can go down to 100 micron perfect. When it's set to 100 micron, the distance to the magnetic coil becomes shorter. So the fuel amount increases slightly. Also, when installing it on the plug side, we bring the cap to the measurement point on the plug side. Then, we check our trigger timing like this. We bring it to the surface. And then before measuring, we take our plate and bring it over. To 0 point, we'll check it. We set the cover in place, then we pull this and let it go. Our measurement here should be 120 micron. That's the required value. Yes, 120 micron is on the plug side. This 120 micron value could also be 110 micron. There's no issue up to 120 or 130 micron. But the ideal measurement is 120 micron. That's the target value. When determining this, the required measurements are explained in detail in the technical drawings. This is the coil side measurement, the square plate measurement. The normal original values are between 110 and 120 micron. We say that the acceptable tolerance range can be between 90 and 120 micron. Dropping below 90 micron is risky as it keeps the fuel level high. It can be considered down to around 100 micron, but we generally don't recommend going as low as 90 micron. After a certain period of operation, the valve seat gradually wears itself down, causing the measurement to slowly drop to around 90 micron or even 80 micron abrasion. But of course, this happens at very high mileage, even a 0.01 wear. When high-quality diesel is used, it drops by a maximum of 0.01 after approximately 150,000 to 200,000 kilometers. With standard installed valves and high-quality diesel, they typically last at least 700,000 to 800,000 kilometers, up to 1 million kilometers. We have working valves. On the valve plug side, the measurements in Mercedes groups, the required clearance in between should be around 110 micron to 120 micron. If the measurements here don't stay within these precise values, the plugs we manufacture separately also have their measurements labeled. We have plugs available in every size. Trigger lengths can be adjusted as needed. We also have square plates available in the desired measurements. In Scania, Volvo, and DF vehicles, the required measurement on the plug side is adjusted, and since the adjustment is tightened with an Allen key, the surfaces are ground parallel. Very nice. Their standard hardness is 30 Rockwell. Even when fully tightened, the threads do not stretch at all, and the tips have additional induction hardening. The tips, where the valve presses, have a hardness between 60 to 62 Rockwell. Their parallelism is at the micron level, and they are highly efficient, with specifications identical to the original. Now, when testing this measurement here is the one referred to as 150. We mounted this approved part in its proper place. When we lightly tighten it by hand, the measurement is 150, and the acceptable tolerance for that is between 140 micron and 180 micron. If we tighten the nut with its normal, original torque, then the required value here is 130 micron. At 130 micron, a tolerance of plus or minus 0.01 millimeters is acceptable. It doesn't cause any issues. The lip thicknesses on the valves in the kits, as shown. It's also written on the side wall of the valve. 0.025 meaning 0.050 millimeters. And up to 150 micron, we have valves with different triggering levels. Why do we do this? Normally, our valves have a synchronized grinding feature. That is, the surface where the plug presses is an angled surface. The surface of the square plate and the third surface work in synchronous. So let's say we removed the original valve. We ground the seat. After grinding the seat, we don't know exactly how much material was removed. We don't know how much we ground off, let's say. There's 7.000. When we look at it with a 0.025 millimeters trigger, the upper trigger values. When it comes in at the normal measurement, The distance adjustment is correct. If it's around 110 micron or 120 micron, and you install it with a 0.025 millimeters trigger, there's no problem at 120 micron. But let's say when we install it with a 0.025 millimeters trigger. If the seat here was ground too much, the square plate will move forward. So, the measurement here, which should be at 110 micron, will drop down to 100, 90, even 80 micron. So what do we do if the measurement drops? If we've ground the seat too much, we'll switch to a 0.050 millimeters trigger. That way, we'll make sure the measurement pulls back. In other words, without changing the square plate, we'll be able to stabilize the required measurement value between the magnetic coil. The same synchronization also applies to the plug, the gap distance in between. Along with the value above, the plug is also retracted. Accordingly, when the standard valve that should be used is applied, the process is completed without changing the top and bottom plugs and square plates. Here, what we need to pay close attention to is important: the measurement. We're talking about the measurement between the magnetic coil and the square plate, which should be 110 micron. And here, if we look at it based on a 6-cylinder setup, and one is set at 80 micron, another at 110, and another at 130 micron, with each adjusted to different values, this essentially affects the start of injection in the car. In other words, what we call the ignition timing, the advance and retard. It marks the beginning of injection at the top dead center of the cylinder. If these values are too close together, like in terms of percentage, let's say, it fires early. When it's at 130 or 150 micron, it fires late. With an imbalanced measurement, the engine runs roughly. You can't achieve that smooth, clockwork-like operation. When we adjust these as well and set it to 110 micron, with a maximum tolerance of 0.02 millimeters. So, for a 6-cylinder engine, when we look at it on that basis, if we're setting it to 110 siren, then all of them should be between 100 and 110 micron. If we're setting it to 110 to 120 micron, they all need to be the same. If it's not set up stably, as we said, the engine will run unevenly. You need to pay very close attention to these things. Now we're going to check the leak test to the pump we've just worked on. That's all we have to explain for now. Yes, we're performing the leak test now. While doing the leak test, we don't use the washer, we do not use stamps. We don't use the square washer you see here. We only installed the valve with its spring, placed the spring, and added the square washer. We placed it in its seat, tightened it into place, and after tightening it, we're performing the test here with the injector gauge. In this leak test, when we check it while it's under its own tension, it shouldn't be leaking under normal conditions. So, normally here we apply 250 bars of pressure, and it shouldn't leak at that level. In fact, it doesn't leak even at 250 bars, and even if you push it to 300 or 400, the system still won't leak. We applied more pressure to test it and tried to make it leak. We pressed it again, and still no leak. Actually, we already tried to make it leak. Now we're turning the valve here and still no leakage. We're turning it again. Still no leakage. We need to test them by turning like this. You can also check it by pulling it by hand like this, or by pressing it from the back with a screwdriver. Either way, the test can be done. This is our final step. Finally, these are the procedures we need to do.